The sun is a merciless tyrant. It glares down. The air is a thick, shimmering blanket. It feels like an oven just opened its door. The road ahead melts into a watery illusion. On the dashboard, a number glows with quiet menace. 50 degrees Celsius. This is not a temperature for machines. It is a number that signals danger. A number that promises failure. Yet the car keeps moving. The engine keeps turning. There is a battle happening under the bonnet. A silent, desperate war against the heat. And somehow the car is winning. Heat is a slow, creeping assassin. It does not announce its arrival with a bang. It seeps into every component. It attacks metal. It degrades rubber. It softens plastic until it loses its shape. It thins the engine oil, stripping away its protective film. It causes metal parts to expand, pushing their precise tolerances to the breaking point. The engine, a marvel of engineering, is fighting for its life. Car manufacturers know this enemy well. They have studied it. They have fought it in labs and in the world's harshest deserts. They design our cars to face this inferno and emerge victorious, even in the brutal, suffocating reality of 50 degrees Celsius heat. Imagine your car's engine as a colossal power station. It is a place of controlled explosions, thousands of them every minute. This furious combustion generates immense power, but it also generates a colossal amount of waste heat. A staggering 2/3 of the energy from burning fuel becomes heat. This heat must be expelled. It must be cast out, away from the engine's delicate core. If it is not removed, the consequences are catastrophic. The engine will overheat. The metal will warp. Pistons can seize in their cylinders. Cylinder heads can crack. The car will die, leaving you stranded on a desolate, shimmering road. The entire cooling system is a story of survival. It is a thriller playing out in silent efficiency. Every part has a role. Every component is designed to withstand this immense thermal load. At the heart of this battle is the radiator. It is the car's cooling champion, the primary hero in this thermal thriller. Outwardly, it looks like a simple metal grille. It sits right at the front of the car, just behind the plastic fascia. It is positioned to face the oncoming wind. Hot liquid, the coolant, is pumped from the engine into the radiator. Air, which is cooler than the liquid, flows over its surface. Heat moves from the hot coolant into the rushing air. The now cooler liquid then returns to the engine to collect more heat. This is the fundamental cycle that keeps the engine alive. To achieve this feat, radiator design is a work of art. They are not simple boxes, intricate networks of thin tubes, even thinner fins. The tubes, usually made of aluminium, carry the hot coolant in a winding path. Brazed onto these tubes are thousands of delicate fins. These fins dramatically increase the surface area that is exposed to the air. Think of it like spreading out a hot dish to cool it faster. More surface means more heat can escape. For cars sold in hot climates, manufacturers often fit larger radiators with a denser fin pack. This design is a delicate balance. The tubes must be wide enough to allow good flow, but narrow enough to transfer heat efficiently. The fins must be dense enough to maximize surface area, but not so dense that they block airflow. Over the years, materials have improved from copper, brass, to lighter, more efficient aluminium. If the radiator is the hero, then airflow is its powerful sidekick. The radiator can have all the surface area in the world, but it is useless without air moving across it. When the car is cruising down the motorway, this job is easy. The car's forward motion forces a massive volume of air through the front grille and across the radiator fins. This constant rush of air is highly effective at wicking away heat. At 100 kilometers per hour, the sheer volume of air passing through the radiator is enormous. This is why a car's temperature gauge often sits comfortably in the middle during highway driving, even on a very hot day. The real test comes in slow-moving, stop-start city traffic. Here, the car is barely moving. Natural airflow drops to almost zero. The engine is still generating a huge amount of heat, especially with the air conditioning running full blast, which adds its own heat load to the front of the car. This is where the cooling fans come into play. They are the car's artificial lungs. Modern cars almost exclusively use electric fans. When a sensor detects the coolant temperature rising to a set point, the computer switches the fans on, creating a powerful artificial wind. These fans are not simple propellers. They are carefully designed aerodynamic devices, blade shape, pitch, size, engineered to move the maximum amount of air with minimum noise and electrical power. Test data from hot climate validation shows weak fans let temps skyrocket at idle. Strong fans keep the temperature under control. The coolant is the unsung hero of this entire operation. It is the liquid warrior, the heat transfer medium that makes everything possible. We often call it anti-freeze, but in a hot climate, its anti-boil properties are far more important. The liquid flowing through your engine is typically a mixture of purified water and a chemical, usually ethylene glycol or propylene glycol. Water itself is actually a fantastic substance for absorbing and carrying heat. It has a very high specific heat capacity, meaning it can soak up a lot of thermal energy without its own temperature rising too quickly. But water has a major flaw. It boils at 100 degrees Celsius at sea level. An engine operating under heavy load in 50 degrees Celsius weather can easily push its internal temperatures well past 100 degrees Celsius. If the coolant were just water, it would boil. Boiling creates steam pockets. Steam is a gas, and it is terrible at transferring heat. These pockets of steam would cause localized hotspots inside the engine, leading to rapid and severe damage. This is where the glycol and system pressure come in. First, the entire cooling system is pressurized. A sealed radiator cap keeps the system at around 15 pounds per square inch above atmospheric pressure. Just like in a pressure cooker, this increased pressure raises the boiling point of the liquid inside. Mixing ethylene glycol with water further elevates the boiling point significantly. A standard 50-50 mix of water and coolant under pressure can have a boiling point of 125 degrees Celsius, or even higher. Desert test data consistently shows that coolant temperatures in a properly functioning system can hover around 110 to 115 degrees Celsius during extreme tests. The high boiling point coolant prevents a catastrophic boilover. It remains a liquid, continuing to do its job of carrying heat away. The cooling system is not just a passive loop, it is an actively managed system. Two key components form the command crew that directs the flow of coolant: the thermostat, the water pump. The thermostat is a simple but brilliant little valve. It acts as a gatekeeper, sitting in the coolant path between the engine and the radiator. When you start the car from cold, the thermostat is closed. This blocks the flow of coolant to the radiator, forcing it to circulate only within the engine block. Once the engine reaches its target temperature, typically around 85 to 95 degrees Celsius, the magic happens. The thermostat contains a small cylinder filled with a special wax that expands precisely at this temperature. As the wax expands, it pushes a piston that opens the valve. The gate is now open. Hot coolant is allowed to flow out of the engine and towards the radiator to be cooled. The thermostat then constantly modulates to maintain a stable temperature. While the thermostat decides where the coolant goes, the water pump is the muscle that gets it there, a centrifugal pump driven by the engine's crankshaft. Its sole purpose is to push the coolant through the entire system, through the engine block, past the thermostat, into the radiator, and back again. The speed at which it pumps is directly related to engine speed. The faster the engine runs, the faster the pump spins. In extreme heat tests, a weak or failing water pump is a common point of failure. If the impeller is corroded or the bearings are worn, it cannot move coolant effectively. The flow slows down. Heat immediately begins to build up in the engine. Manufacturers for hot climates specify heavy-duty water pumps, more robust bearings, more efficient impellers to survive constant high-temperature operation. Together, the thermostat and water pump form a dynamic duo, directing and driving the lifeblood of the engine. That's basically how they work. The battle against heat is not just fought inside the engine, it is also fought on the car's exterior and under its skin. The design of the car's front end manages airflow. Active grille shutters close for aerodynamics and open wide when temperatures climb, or you're stuck in traffic. Plastic ducts, shields, and underbody panels create high pressure in front of the radiator and low pressure behind, sucking air through and feeding the AC condenser and transmission cooler. Heat shields protect sensitive components from the radiant furnace of the engine and exhaust manifold. Automotive engineers do not guess when it comes to heat. They test, in labs and in the harshest environments on Earth. Proving grounds in the Middle East, proving grounds in Arizona, proving grounds in Australia. Cars face torturous cycles in ambient temps regularly above 50 degrees Celsius. Vehicles are fully loaded, sometimes towing, bristling with sensors logging hundreds of data points every second. On the highway in 50-degree heat, coolant stabilizes around 105 degrees Celsius. The radiator drops about 10 to 15 degrees each pass. In city idle simulations with AC, air in front of the radiator rises above 70 degrees. Coolant can climb to 118. Fans roar at maximum to hold the line. Block the radiator or use degraded coolant and failure is swift. Coolant shoots past 125. The cap vents steam, hoses swell and burst. Data drives fixes, larger radiators, stronger fans, premium hoses. If the gauge creeps to danger, turn off the AC and set the heater to full to shed heat. Pull over safely, open the bonnet, but never open the radiator or reservoir when hot. The pressurized system can erupt and cause severe burns. Wait 30 to 45 minutes before checking anything. So the sun beats down, the asphalt turns soft, the air is a physical weight, yet your car keeps running. It survives the 50 degrees Celsius crucible. This is no accident. It is the result of over a century of engineering, brutal testing, continuous improvement. A victory won by a team of carefully designed components, all working in concert. The foundation is designing with a large safety margin, not for the average day, but the absolute worst day. Radiator. Large, efficient, max surface area. Fans. Powerful, reliable. Coolant. High boiling point. Water pump. Robust. Thermostat. Smart and simple. Ducts and shields. Guide and protect. Shutters. Control airflow. Electronics. Monitor and adapt. Engineering is only half the story. Check coolant level. Replace coolant on schedule. Keep the grill clean and act at the first sign of trouble. Simple preventative checks can be the difference between a smooth journey and a roadside disaster. Replace fear with quiet confidence in the machine. Under the bonnet, a silent, relentless battle is being fought and won. The heat is pushed away, the engine breathes, the pistons continue their dance. The car is built to endure, a testament to human ingenuity, a complex machine operating reliably in a hostile environment. Next time on a scorching day, appreciate the invisible, life-saving thriller a few feet in front of you.